Gonna do one more centripetal acceleration example, but this one's gonna be horizontal. Here it is. I have a block on a table, and we can even make this a frictionless table, and somewhere in the table a hole has been cut. The block is attached to a string that passes through the hole in the table and to another mass. This block has a mass, let's say 4 kilograms. Let's call this one m equals question mark, and the block is going to be allowed to move in a circle. So looking at this table from above, what I would see is the block moving in a circle, attached to a string. The string passes through the hole in the middle of the table. And that's it, really. This block is moving in a circle. I'm going to need a length of string, so let's call the length of this string 1 meter. And actually, instead of saying we don't know the mass of this block, let's give this block a mass. We'll give this block a mass of 2 kilograms. And then we can ask, how fast is the block moving? Now what I know is that if this block isn't moving at all, if I just set the block there, it's going to slide inward, and that's going to be the whole thing. This block is moving, and if it's moving fast enough, then it's going to be able to maintain moving in a circle at a constant speed without falling down. And you know this if you have ever taken like a string in one hand and swung it around, like a string with a ball in one hand and swung it around in circles. If you just let go, it's going to go flying away. If you slow down too much, it's just going to drop. So there is some speed where you can hit that steady kind of sweet spot. I'm going to draw a free body diagram for the block. For the block, what I have going on is a force to the right. It is the only thing going on, and it's moving in kind of this path. So I'm going to call that my positive x-axis, and that's my free body diagram for the block. Now, the triangle, that one's going to matter. This triangle, if the block moves to the right, which I said was my positive x-axis, then this triangle moves down. So downward has to be the positive x-axis for the triangle. So for the triangle, which has a mass of 2 kilograms, the triangle feels a downward force of its weight, and it feels an upward force of the tension. And I said downward is going to have to be my positive x-axis. Okay, a quick note. This picture right here is the top-down view of this block moving in a circle. When I do that, I do get, there is another force, right? Like there are 2 more forces. The weight of the block pulls it down, which would be into the table, and the normal force pushes it back up, keeps it from falling into the table. Those would be perpendicular to this table. This whole square is like the shape of the table. So I could say that there is a normal force that comes out of the screen at me, and a gravitational force that goes into the screen away from me, but those are going to cancel, and I'm not worried about that direction, that whole dimension anyway. So I'm just not going to do it. All right, for the box, my sum of forces in the x direction are t. That's it. Sum of forces has to be equal to mass times acceleration. My acceleration is not 0. This thing's moving in a circle. It's moving in a circle. There's the middle of my circle, so I know I'm going to get a centripetal acceleration. And a centripetal acceleration always has a magnitude of v squared over r. It points to the right because that's where the right or the center of my circle is, so it is going to be a positive value. So what I get is t equals mass times v squared, v is what I'm looking for in the end, over the radius of my circle. If I go back to my picture, radius of my circle is just L because it's the length of string. T is mv squared over L. And that's good. Two unknowns, so I'm going to have to move on to the triangle. If I look at my sum of forces in the x direction there, what I get is mass of the triangle. I'm going to call these mass 1, mass 2. So those are mass 1s up here. I get mass 2 times gravity, that's in my positive direction, minus tension in my negative direction, equals mass 2 times acceleration. The acceleration of this guy is actually going to be 0. Where the block is moving in a circle, so the direction of its velocity is changing, the triangle is just hanging still. It's not moving up, it's not moving down. This guy's going around in circles, right here. It'll be like that kind of thing. But this one is staying put. So the triangle has an acceleration of 0. Which means this equation becomes m2g equals t. Well, I can run with that. I'm going to put that in here. And that gives me m2g. Remember, that's what t was. Equals m1 times v squared over L. I'm looking for v. V equals, I'm going to get m2 GL divided by m1 and all under a square root. If you are not sure how I got here, take a second and work that part out. Make sure you convince yourself that that's what v would actually be. So m2, 2 kilograms, 10 meters per second squared. My length, which was I think 1 meter, it was 1 meter over m1, which was 4 kilograms. All under a square root. V works out to be about 2 1/4, a little bit less. It's going to be 2.23 meters per second. That's how fast I'm moving for this thing to stay steady. That's the whole problem.